Okay, let's dive into this problem about an electron moving through electric and magnetic fields. So here's the question we are looking at. We have an electron and we are given its mass, which is 9 times 10 to the power of minus 31 kilograms, and its charge, which is 1.6 times 10 to the power of minus 19 coulombs. This electron is moving at a speed of c over 100, where c is the speed of light. It gets injected into a magnetic field, let's call it vector B, with a magnitude of 9 times 10 to the power of minus 4 Tesla. This magnetic field is perpendicular to the electron's direction of motion. Our goal is to figure out what kind of uniform electric field vector E we need to apply together with this magnetic field, so that the electron just keeps going straight without deflecting from its original path. We are given the speed of light c as 3 times 10 to the power of 8 meters per second. Now let's look at the options provided for this electric field. We need to figure out which of these is correct. Alright, let's think about the solution. To make sure the electron doesn't deflect from its path, the total force acting on it has to be exactly zero. This means the electric force, which we'll call vector Fe, must perfectly cancel out the magnetic force vector Fb. So mathematically we can write this as the vector electric force plus the vector magnetic force equals 0. Let's start by calculating the speed of the electron, which is step 1. We know the speed of light c is 3 times 10 to the power of 8 meters per second. The problem tells us the electron speed v is c divided by 100. So we calculate v by taking 3 times 10 to the power of 8 meters per second and dividing it by 100. This gives us a speed v equal to 3 times 10 to the power of 6 meters per second. Next, in step 2, let's figure out the magnetic force acting on the electron. The formula for the magnetic force on a charged particle is vector Fb equals q times the cross product of vector v and vector b. The magnitude of this force is Fb equals the absolute value of q times v times b times the sine of the angle theta, where theta is the angle between vector v and vector b. The problem states that vector b is perpendicular to vector v, so the angle theta is 90 degrees. The sine of 90 degrees is 1. This simplifies the magnitude of the magnetic force to Fb equals the absolute value of q times v times b. Continuing with step 2 for the magnetic force. We are given the charge of the electron. Its absolute value AQ is 1.6 times 10 to the power of minus 19 coulombs. The magnitude of the magnetic field B is 9 times 10 to the power of minus 4 Tesla. And we just calculated the electron speed V as 3 times 10 to the power of 6 meters per second. Plugging these values into the magnitude formula, Fb equals 1.6 times 10 to the power of minus 19 multiplied by 3 times 10 to the power of 6 multiplied by 9 times 10 to the power of minus 4 newtons. We can group the numbers and the powers of 10Fb equals 1.6 times 3 times 9 multiplied by 10 to the power of minus 19 times 10 to the power of 6 times 10 to the power of minus 4 newtons. Calculating this gives us Fb equals 43.2 times 10 to the power of minus 17 newtons. Now for step 3, determining the condition for no deflection. As we mentioned before, for the electron to not deflect the electric force vector, Fe must be equal in magnitude and exactly opposite in direction to the magnetic force. Vector Fb. This is represented by the equation vector Fe equals minus vector Fb. This equation directly implies that their magnitudes must be equal. Fe must equal Fb. Moving to step 4, we'll calculate the magnitude of the required electric field. The electric force on a charged particle is given by Fe equals the absolute value of Q times E, where E is the magnitude of the electric field. Setting the electric force magnitude equal to the magnetic force magnitude as required for no deflection, we have the absolute value of Q times E equals the absolute value of Q times V times B. Since the absolute value of Q is not 0, we can cancel it from both sides, giving us a simple relationship E equals V times B. Let's continue with step 4 to find the electric field magnitude. We substitute the values we already know. For V and BV is 3 times 10 to the power of 6 meters per second. B is 9 times 10 to the power of minus 4 Tesla. So E equals 3 times 10 to the power of 6 meters per second multiplied by 9 times 10 to the power of minus 4 Tesla. Multiplying the numbers and the powers of 10, E equals 3 times 9 multiplied by 10 to the power of 6 times 10 to the power of minus 4 volts per meter. This calculation gives us E equals 27 times 10 to the power of 2 volts per meter. Now let's figure out the direction of the electric field in step 5. To do this, let's assume a simple coordinate system. Let's say the velocity vector vector v is along the positive x-axis and the magnetic field vector vector b is along the positive y-axis. The magnetic force is given by vector Fb equals q times the cross product of vector v and vector b. Using the right-hand rule, the cross product of vector v along path x and vector b along path y is in the positive z direction. However, the electron's charge q is negative. So the magnetic force vector Fb, which is q times that cross product, will be in the negative z direction. Continuing with step 5 to find the electric field direction. For the electron to not deflect the electric force vector, Fe must be in the positive z direction, exactly opposite to the magnetic force. The electric force is given by vector Fe equals q times vector E. Again, since q is negative for vector Fe to be in the positive z direction, the electric field vector E must be in the negative z direction. It has to point in the opposite direction of the force for a negative charge. Let's summarize the directions in our chosen coordinate system for step 5. We assumed vector v is along the x-axis, vector b is along the y-axis, and we found that vector E must be along the z-axis or the negative z-axis, but parallel to the z-axis. Looking at these directions, vector E is clearly perpendicular to vector v, and crucially vector E is perpendicular to vector b. Therefore, we can conclude that the electric field vector E must be perpendicular to the magnetic field vector b. Now in step 6, let's compare our findings with the given options. We calculated the magnitude of vector E to be 27 times 10 to the power of 2 volts per meter, and we determined the direction of vector E must be perpendicular to vector b. Let's look at the options again. Option 1, vector E is parallel to vector b, magnitude is 27 times 10 to the power of 4. That doesn't match. Option 2, vector E is perpendicular to vector b, magnitude is 27 times 10 to the power of 4. The direction matches, but the magnitude doesn't. Option 3, vector E is perpendicular to vector b, magnitude is 27 times 10 to the power of 2. The direction matches and the magnitude matches. Option 4, vector E is parallel to vector b, magnitude is 27 times 10 to the power of 2. The magnitude matches but the direction doesn't. So based on our calculations, our values match option number 3 perfectly. The magnitude we found is 27 times 10 to the power of 2 volts per meter, and the direction we found is perpendicular to vector b. In conclusion, the correct option that describes the required electric field is option 3. The final answer is option 3.